That doctor had a colleague at Michigan who contacted him and contacted Glenn, and they said, would you agree to try to make a mask for the king, right? I was at a meeting and he called me up again and said, oh, how would you like to go to Saudi Arabia? I had no idea what he's talking about. Oh, he said.
Welcome to HolyShift, Biomedical Breakthrough Shaping Tomorrow. What is biomedical engineering exactly? It's about engineering solutions that improve human health, from new medical imaging tools to personalized cancer treatments. HolyShift reveals the people, passion, and purpose powering the future of biomedical research. I'm here today with Dr. Scott Hollister, the Patsy and Allen Doris Chair in Pediatric Technology and Professor of Biomedical Engineering at Georgia Tech and Emory. Scott's work is all about using 3D printing to design medical devices that can literally save lives. From custom implantable airways for children to specialized CPAP masks for patients around the world. Please welcome the brilliant mind helping shape the future of personalized medicine, Dr. Scott Hollister. Well, good morning, Dr. Scott Hollister. Thank you for joining us here today.
Good morning, Angela. It's nice to be here.
Okay, I'm loving this. I'm very excited because I know pieces of your story.
Yeah.
The audience doesn't know it yet. Yeah. And so I would just tell everyone, go ahead and get prepared, get some tissues near you, and get excited. Yeah. So why don't we kick off?
Okay.
And tell us about your research, but from like a big picture perspective. How would you describe the work that you do?
Yeah, I would say our work we're trying to develop through the use of 3D printing, which I think most people are familiar with now.
Yes.
Medical devices, especially for kids, for pediatrics, where you might have sort of one-off needs for a medical device. And I think 3D printing really gave us the capability to do that on a really customized basis. So our whole, I think, goal or focus of our research is to have the capability if a clinician comes to us and say, hey, I have this case, could we develop a device for this kid? And that's sort of the way I got started in doing this, actually.
Okay, so I want to dig a little bit earlier on this. How did you decide? Because I know of a couple of these instances that you've done, and they're amazing stories. I cannot wait. We're going to do teasers. Listeners, you have to keep listening to hear these. So how did you get into biomedical engineering and into this line of work? I say this often, when you're in elementary school and they ask you, what do you want to do when you grow up? Yeah. Was it along those lines, or how did you get interested?
No, I mean, the story of how I did my undergraduate in aerospace engineering, actually.
I did not know this.
The
Wow.
University of Michigan.
So it is rocket science, is all I want to say.
Yeah, could be rocket science. But at that time, that was the early 80s, and like NASA had sort of gone down, and really the only jobs available for aerospace engineers were in defense industry, and I didn't want to do that. I wanted to do something maybe more positive for humanity in a way. And then I decided to go to graduate school, and I switched into combination of bioengineering and mechanical engineering.
Okay.
And that's how I got into it. And then when I did my PhD, he wasn't my main advisor, but I had an advisor, a professor at Michigan. He was Japanese, and he was super famous and well-known in automotive. And I liked what he did. He was coming up with new ways to design very complex structures. And, he wanted to have a way to build these, to manufacture them, because there was no way to do it. They were so complicated. And that's how he got into 3D printing. And he told me, hey, I'm doing this to build these structures for automotive, but, you deal with complicated structures in bioengineering. You should look into this as a way to do it. And that's how I really got into 3D printing, was through his influence, actually.
I love that, because we forget, we talk a lot on this podcast about the impact of having diverse thoughts and people from different multidisciplinary backgrounds and how they can inspire breakthroughs. And this is a perfect story. Something coming from a completely different industry.
Yes.
transitioning into healthcare.
Yeah.
Okay, so let's continue the journey then. So you thought about this. Now, were you already? So this is when you were a PhD student, okay, and you hadn't set up your lab yet. So when you were setting up your lab, was the premise of doing these specialized patient-specific 3D printing, or was there something else that tied to it?
No, I mean, when I went after I graduated into the medical school at Michigan in an orthopedic research lab, and I was doing mainly sort of bone mechanical properties and things like that. But I was always interested in, I'd worked with this professor, and I was always interested in design and trying to design implants and be able to make them. So I was always interested in working with clinicians and figuring out problems and doing this. And that's, at that point, I started to interact with clinicians even outside of orthopedic surgery, mainly in like cranial maxillofacial surgery, because, facial structures are very complicated and building implants is very difficult. And they had these complex cases where they were trying to reconstruct, like your temporal mandibular joint or part of your face. And that's how I really got into the idea of how do we take, you really need patient-specific structures. How do we take image data and convert it into a form that we can print, right? And that was really my first work in the area. So that was mainly computational work, like how do you read medical images, do design with them, and output them. Now we have lots of software to do it. Back then we didn't. We had to just sort of write it from scratch.
Well, and I can even think of an example of a patient, for example, that has a horrific auto injury and has to have significant implants. Like every face is unique in and of itself. Yeah. And so the idea that you would just go to a shelf and pick a jawbone or pick some, right? And it actually be able, because really the compassion of restoring a human life to as close as you can get to before their incident is so huge. Yeah. So that work is so impactful.
Yeah. And but like you said before, it brings in many threads, right? It's not just design, it's material science, it's manufacturing, trying to understand, for example, now you give the example of jaw reconstruction due to cancer or trauma. And the sort of go-to method now is they take a piece of your leg bone out, right, your fibula. They cut it out with a blood vessel. They try to cut it up to make a jaw. They implant it with plates. They take that vessel and they hook it up to vessels in your neck to make sure it has blood flow, right?
Wow.
So.
And do you have any idea of how long a surgery like that would take?
It usually takes 15 to 20 hours, right?
Right. Wow.
Because you have to, you need two teams, right? You need one team to harvest the fibula,
right,
and the blood vessels, and another team to open up the face and do the reconstruction, right?
Wow.
So there are alternatives, 3D printing, and that's been sort of a holy grail in some ways, is how do we get blood flow into these things, right? You always need blood flow to keep cells alive and all that.
Which I think is important for us to understand, because we could think if we're not in that field, we think of bones. We don't understand the blood implications within that and how circulation is so important for it to continue to be alive and all those pieces. And so you might think, well, I could just put a piece of plastic to fill a space there. So continue why that does not work.
Yeah, because, to regrow the tissue, right, the plastic is going to fail after a while. And that's another unique aspect of this field, right, is if we can get away from it, we don't want to use permanent materials. We want to use materials that resorb and go away, and the tissue will fill it in to have natural tissue. So ultimately, these materials are going to fail, and you need tissue to replace them. You can't just put cells in there. If they don't have blood flow or nutrition, they're going to die, and it's going to necrose, and a lot of yucky things will happen. So you need blood flow, and that's really a huge challenge in the field. And one interesting thing, given that we're just past Halloween, it sounds sort of like Frankenstein, is to print a device, implant it in a muscle, let it cook there for a month or so, and get blood vessel growth, and then transplant it.
Yeah,
so what that does is, instead of cutting out a piece of your leg that you have to cut up further to match. You have something already matched, and the surgery is not, to harvest it is not as morbid in a way.
Right.
And then you can just transplant it. And that can be done for a lot of people. Actually have done that or attempted that in patients. It's gone okay, but trying to advance that is a real interest.
Well, that's huge, because I can also think about just the recovery time of a patient that has had a piece of their bone, their leg. So now their leg has issues trying to recover, and potential complications in the leg. And the space that's being repaired has to recover, and potential implications of that piece.
Yep.
And the medical cost of a surgery of that level versus, I would imagine that this type of approach, first off, you're significantly reducing, you're not, removing any instance of the leg. You have less complication risk if you can perfect it, right? And then the overall cost to the individual, to the healthcare system, to the government, everything is significantly less.
Yes.
And you get a better output.
Yes, that's all of those are correct. That's the goal, right? And some patients actually can't endure that type of surgery, right? I mean, being on the table for 15 or 20 hours is really tough on your body. So this might increase the pool of patients that could have these procedures, in fact. And the other thing we don't think about is the reason, going back to the blood flow, is, often you get, radiation for these types of tumors, and that further degrades the blood flow into that area. So that's another issue that has to be dealt with.
Okay. So tell us about some of I know of a couple of the major successes that you've had. Tell us about a couple of those.
Yeah, I think the biggest success we've had is going back to kids with treating collapsed trachea or airway, basically, or trachea in your bronchi. There's a condition, it's not...
And for those that don't really know where the trachea and bronchi are,
so if you feel your throat, right, this is your larynx up here, you can feel it, and then it goes down, and that's your trachea, which is your main branch of the airway, and then it will branch out right into two main stem bronchi, we call them, and then it keeps branching out into your lungs. But
basically, if it's not working well, you're not breathing.
Yes, exactly.
Okay. Yes.
And so in kids, there are lots of anomalies. They might have their aorta, instead of going out, it might be wrapped around their airway as a ring. They might have enlarged other vessels coming off their heart, and those compress the airway. And the airway is made out of cartilage. So if you actually feel the end of your nose, right, that's cartilage. And your ears are cartilage, and your knees, the different types of cartilage. And that's what gives the airway its structure. So what happens in this case, we think, is these other structures sort of impede the airway, and it can't grow, and those cartilages become sort of floppy and soft. So when the child tries to exhale, it creates a negative pressure, and that normally the cartilage would be stiff enough, and it shrinks a little bit, but then when you breathe back in, it goes up. But in these kids, it collapses completely, right? So they can't get any air in or out of that lung, and they tend to have respiratory distress. And in fact, going back to the whole story, when I was at Michigan, there was a pediatric otolaryngologist. He was a specialist in tracheal reconstruction in kids, and he dealt with a lot of these cases. So the way that they treat them at that time is you would do a tracheostomy, so you would cut a hole in the kid's throat, put them on a ventilator, right?
Oh.
And you have to get them out like a year or 2 years for these cartilages to develop enough to keep the airway open.
So they would be on a ventilator for that period of time?
Yes.
And I think as a consequence of COVID, we're all learning in society the negative impacts and how ventilators are not good things.
Yeah, exactly. And they create issues, right? Because once you cut a hole in these cartilage, that softens the airway as well. And there are lots of additional, due to COVID and people being on ventilators, tracheal issues that we'll probably see going forward.
Yeah.
And this, going back to the surgeon, there was a business, development officer for the Department of Surgery, and she introduced us, and I told him, we could do some at that time we had done some 3D printing of biomaterials, and I said we could do that. And he said, well, we have this condition that if you could create something for that, it'd be really great for us, right? And I did some design work and didn't think about it. And unbeknownst to me, he had gone off to some meetings and say, hey, you have these patients, we can do this. We can do this.
I love this.
Send them to us.
Yeah.
And then he called me up and said, hey, are you ready? We have the first patient. We're going to fly them to Ann Arbor to do this, right?
Oh, wow. So this is when you were still at Michigan.
Yes, when I was still at Michigan. And then I said, the only thing we had done at that point, we had done some of this work in large animals for spine fusion. And I said, we can give it a try. And I had not done that. So we had to scramble. And the university at that time, the medical center there was, they were covering the liability. And they said, oh, do you have FDA clearance? I said, no, we don't know anything. And, we have to come up with a way to, sterilize the device and all this. So I'm calling around and people are telling me, you're crazy. So I finally found one company that would do it for us, that would sterilize it and test it.
Which I think all great breakthroughs, somebody has said you're crazy at some point. So when you hear that, that's probably good inspiration.
I remember it very distinctly. I was in my office at Michigan. It was like 5:30 or 6 in the evening. I was calling around to all these sterilization companies to try to. And fortunately, this one was in Utah, so they were a couple hours behind us, and there was still somebody in the office. So I got them to do it, and we built it and got it sterilized. And, at that time for these devices, this was all humanitarian emergency use and clearance by the FDA. It's not an approved device. And he just called them up and they said, okay, we're going to sit down and talk with you for 15 or 20 minutes and tell us how are you making this device and all this. So we did that.
That was what the FDA said?
FDA.
Yeah. Yeah, because I think so that the audience understands is there is a regulated pathway to get things that are approved that can be approved for patients from all different stages. And we go through these clinical trials. And yet there are also pathways that are emergency pathways where you can have something like this so you can save someone that cannot wait 20 years.
Yes, exactly. So in those cases, if there's nothing out there on the market to treat these patients, which there isn't, you can go to the FDA and say, this is an emergency. This child will likely die. So this child, they flew him into Ann Arbor, and he was in the ICU, the NIC ICU. And we got approval, and we made 15 or 20, right? Because we did it from images. So the previous work, looking at being able to design from patient images, we could use that. And I designed it from that, and we printed it and got it put together, and they took it in the OR, and then they did the surgery. And that sort of garnered a lot of press, right? Because people had done some 3D printing of devices, but nobody had done it in an emergency case and implanted it, and it saved this kid's life because he would have died. The story was he and his family, he was a toddler, 3 months or 2 months, was out at dinner, sort of, his kid couldn't breathe right, and he gave him mouth to mouth in the restaurant to save him.
Wow.
And that's how it happened.
Wow. And so, so that happened, and then everyone went into full steam ahead. Like, how can we fix it? One of the things this reminds me of, I started my career at Medtronic when I hear the early stories like Earl Balkin and the pacemaker and the hospital, like them being up in Minneapolis area and the power going out in the area. And you have these pacemakers that now are not, and they come up with here, let's do this. And that's how some groundbreaking breakthroughs happen. Yeah.
It was just sort of a lot of, perfect storm thing that a lot of issues came together at once. And the surgeon was, he was really visionary. He wanted to push this forward. And the university, I have to give them credit, right? Usually I have to say universities tend to be very conservative in this way.
Right, because the risk is high.
The risk is high, and it's a lot of liability, but they, we had it in our lab, right? We didn't have any special clean room or GMP to build it.
Right.
And we had to figure it all out. But they supported it and it went forward.
So with that, then tell us what happened with the child.
So he survived, right? And he was patent, the airway, patent means it was open, he could breathe. And now I think he's like maybe a junior or senior in high school. He just
That's so
texted
amazing.
me pictures of him. But yeah, and then, he contacted the New England Journal of Medicine and said, we did this. And they said, oh, this is good. This is great. We're going to hold off for a year to see how things turn out. We're still going to.
We don't want to publish anything.
No, they said they would still publish it, but we want the follow up. Of course. So we waited, and it was embargoed, so we couldn't talk about it at meetings or anything. And then,
how hard was that? Because it's just so inspirational. I would think I would want to tell everyone.
Yeah, I mean, they didn't mind that there would be news stories about it.
Right.
I don't know if they. Yeah, I think we had news stories about it before then. But yeah, we waited a year, and he was the patient we followed the most. We published, he was in maybe 2 or 3 papers. We followed him, and I felt, sort of his parents, the good thing they were in Ohio, so it wasn't a long trip to Michigan. But they would come up to Ann Arbor, and he would get CT scan. This is the first one, and we'd follow how does the airway grow? Is it growing normally, and things like that. But the first paper we published in the New England Journal of Medicine, that was 2013. Yeah, I think it was all embargoed because I think the press didn't come out until the New England Journal was published.
Oh, wow.
And then we got a lot of interest and things like, it was on the Today Show and they sent a reporter into the lab and all
Okay,
that.
so my favorite review is any links you have for any of this that we can include in the show notes.
Yes.
To the audience, we will do that.
I'll send you all the links for that.
Amazing. Because that's so powerful.
Yeah.
So how did you get from Michigan to Georgia Tech and Emory?
Yeah, so I think based on that, and a lot of things happen in these moves, and I think Children's wanted to do it as well. So there was a bit of a split because there was a company that wanted to do it in Michigan, and we changed the design. I came to Children's, and we did some cases here, and I still work with my colleague Glenn Green at Michigan, and in fact. Not to jump ahead too much, but after I came to Tech, there was a girl, she was in Pennsylvania actually, and she was in the Penn State Hershey Medical Center, and she was born with a very rare condition called tracheal agenesis. So she didn't even have a normal airway with cartilage and everything. What she had was her esophagus, the tube we swallow through, is formed, and then her bronchi come off of that.
Oh, wow.
So
it would almost be putting food into the lungs if that were even to be a possibility.
They actually have to disconnect
the
esophagus from your mouth, essentially, and they feed her intravenously for a while. So what they did, and this was all involved, so I was here at Tech, and then the Penn State surgeon had trained at Michigan as a pediatric surgeon, and he knew Glenn. So we were all connected then to do this case. And in that case, we used a splint, an airway device, to make the esophagus into an airway. So they put the device, because the esophagus is too soft to withstand respiration, in and out breathing. And so they put the device around the esophagus and brought it out through a stoma in her neck. And then she could breathe through that.
Wow.
And to date, I don't think any child with this condition has lived past 12, but she's probably, I think when she had it, again, she was very small, maybe under a year old. They did the surgery at Penn State. She's now 7, but there was a follow-up surgery, right? So
yeah. Because she's not still being fed intravenously, or
yeah, I think they did some reconstruction so she could eat, but she can't talk, right? Because she has no air going through her vocal cords.
Oh.
So she had part of her larynx, right? So this cartilage up here is where our vocal cords are, and we are able to speak because we can force air through them and they vibrate and we can make sounds. So she can't do that because her air is coming in through her stoma.
Yeah.
So his goal, and we'll see how it turns out, say, I want to rebuild her larynx, and then she can talk, or she can learn to speak maybe. So in this case, this was maybe 6 months ago, and he said, we can have the company build it, but he said, I came to you because I want you to design it right. So this is a new device. It's like a combination of larynx and trachea with a hole in it. So he could route the esophagus back up into her larynx and rebuild part of her larynx right. I don't know if I should talk about this or not, but anyway, I mean, he's done that surgery. So, sort of circling back, I think that's the power of this approach, right? Because you can design things from a patient, you can print these of biomaterials, and you can make devices that don't exist, on the market. So you can make these specialized devices for kids.
Right. And having a way to where you have a mechanism where you can specialize them, but you also then have the connections so that you can do the sterilization, so that you can do all the things to make sure they're safe and effective, and can then broaden the audience that can have access to these type of things. So let's talk about the work that you're doing now, and how is that funded? How, who is it that, because these are one-off, so it's a little bit of a different situation than if you were perhaps creating something that 10 million people would use.
Yes, exactly. So we, most of our funding comes through NIH, and we try, there are a lot of open issues with these things, right? Like, when we use resorbable materials, this idea of regenerative medicine or tissue engineering has been around for a long time, since the late 80s. But there are some fundamental things we don't understand, like how do these materials resorb, and how do their properties change, and how does that affect? And in kids, the huge thing is growth, right? Because we put these devices in around their different organs. We don't want to impede the growth, right? So we have to understand, in animal models or whatever, how do these materials degrade, and how do the animals grow? And we want to make simulations for that, right? Because we can't, once we do these in patients, we don't want to go back. We don't go back and take the devices out.
Right.
And animal models, we use them, but they grow at a different rate. So we want to combine all this information, the patient data, the animal data, with, simulations and probably even AI now, to figure out, can we predict, if we put a device into a patient, how will they grow? How will the device function? So we're trying to incorporate all that together, and that's all funded through the NIH, and some of it through the NSF. We got grants, and in fact, the reason we could build this device for the first child is we had funding from NIH for this cervical spine fusion work. So even though it was work in another field, right? The fact that the government had funded it, and we had perfected a lot of the manufacturing techniques and understood that the material is biocompatible and tissue can grow into it, that enabled us to do this other device and go into another field.
I'm so glad you said that, because that is the other piece, is that sometimes we forget, and it's easy to say, oh, wait, well, why are we going to spend this amount of money on one human life? First off, also, what's the value of one human life? Like, we know it's a lot. Okay.
Well,
but you could still
kid,
look at that.
Course.
Right.
Yeah,
exactly. And so, but we forget that every time we do that, the things that we learn and that all of the breakthroughs that happen in that instance then fall into like 10 different categories, or I'm just, all these different categories. They can advance the science in those other categories as well. So the long-term impact is so huge in this.
Yeah, and that's our goal, really, to try to branch out and use this. So I'm actually talking at the Pediatric Health Summit this afternoon about...
I'll see you there.
Yes. We're making devices in a lot of areas: cardiovascular, vascular repair, craniofacial, orthopedics, and, the head and neck as well. But, getting funding from the government to do this allows us to spread into other areas. So, and there are a couple of things, in terms of the impact. Obviously, it's your children, and we're fortunate most children are born healthy and they grow up healthy. But for the ones that not, it's a big, huge emotional burden on the families and a financial burden, right? I mean, having a kid on a ventilator for a year or 2 years, that's easily $1 million per child.
Yeah.
And not, let alone the fact, the family has to be there, the child can't go out, they can't go to school. That's a huge impact. So being able to do this can reduce our healthcare costs, I think, as well as, improve, quality of life. And we can spread it to other areas. Like we developed a interesting shape memory material that we now can 3D print that you can print in one form, compress it, fold it up, so you can put it in minimally invasively. And then when it warms to body temperature, it'll refold into its original shape.
Oh, that is so cool.
So that we're looking at for cartilage repair, for arthritis. So not just kids, but older adults. But we've used it in, we haven't used it in patients yet. That is our goal. So we have some, and we've applied for NIH grants to use it for tracheal stenosis, to use it for nasal septal repair. So a lot of people have nasal septal issues, about 1 to 2% of the population, and probably about 1% of those are symptomatic enough that they need surgery.
Yep.
Still, that's 30 to 70,000 people a year in the U.S.
Yep. Okay. So sorry, audience, we're going to go a little long on this interview because there's a story I want to make sure we don't miss, because there are one-off instances and there are one-off life experiences. Yeah. And I know you had a unique experience to be able to create something as a one-off. Tell us more about it.
Yeah. So because of this work with Glenn Green, and it's a roundabout thing, but there was a clinician at Michigan who knew a clinician at New York who was, so the king of Saudi Arabia, who has since passed, he was the older king. He had a lot of American doctors, and he had a sleep specialist in New York, and they said, if he needs CPAP, and they couldn't get one that worked right with him. And that doctor had a colleague at Michigan who contacted him and contacted Glenn, and they said, would you agree to try to make a mask for the king, right? So, and that's sort of a specialized thing, because he said, okay, they want you to be there, right? So they're going to take you and all your colleagues and residents, and they're going to fly your group to Riyadh, Saudi Arabia. And I was at a meeting, and he called me up again and said, oh, how would you like to go to Saudi Arabia? And I had no idea what he's talking about. Oh, he said, the king has this issue, and they're going to pay for us, and they're going to buy printers to bring over with us to do this. And it was a funny story because, and they put us on Saudi Airlines in business class. So we had to fly out of Dulles. So we had to fly from Detroit to Dulles. And the one thing was that, I don't know, somehow we were waiting for a material or a printer. And they said, somebody has to go back and get that. So the rest of them flew out. And I flew from Detroit to Dulles, back to Detroit, got the thing, flew back to Dulles, and then I flew to Riyadh separately. And they put us, up in a hotel, and the king would work at night. He would work from like 6 or 7 in the evening till the morning. And he had multiple palaces, and they would come pick us up in the afternoon from the hotel and take us there. We sort of set up a lab in a room in his palace, right? And we would work on this, and, he would be working, and they would come to us every night and say, oh, we may take you to see the king tonight. And then it wasn't happening. Then one night we did, and it was like 3 o'clock in the morning, and we would work through the night, right, and then sleep during the day at the hotel. And they came in, and I remember it's, of course, very elegant and everything in the palace. And it was a huge table, and he was sitting there, and we had an interpreter, and we would talk to him and talk about his issues. And we were making this mask for him and printing. We did end up being able to print some, masks that he was able to try. So, but it was just an amazing thing about how all these connections came up. And, at that time we couldn't say anything to anybody. And,
right.
I mean, my wife knew, and they were like, they gave us special, you can only use this phone when you're here. You can't use your regular phone.
Right.
So it's just an amazing story. And when I flew to the airport, right, I met a bunch of Americans because they were all the physicians that they were flying in, and they would pick us up at the airport to go to the hotel. And it's just an amazing story that this would happen based on all of this and all of the publicity that came out of the pediatric case.
Well, I think, too, that it's something that we as Americans don't realize how proud we should be of the amount of advances and the research that we have in the U.S.
that are making impact across the entire world. We talk a lot about that in my master's class in the global therapeutics, is that we're really the epicenter for advancement and innovation and entrepreneurship. And I also, the other piece I love about the story is that I think we sometimes think that like kings and queens are just like sitting on their throne, right? And he's working this whole time. And the only time he's not is at this period of time. And so that type of collaboration and being able to keep those things going is huge. So thank you.
Yeah, exactly. Because he's the head of the state, right? He has to deal with the government affairs. But yeah, that's very, you hit it right on the nail in the fact that he brought over these specialists. They were trained in the U.S. and they got this training because of the funding of the U.S. healthcare system. I think a lot of people don't realize that the government funds training of residents who become their doctors, right? That's all funded by the government. And a lot of these residents that learn to do research, they get supported by training grants that are supported by the NIH. So it all not only affects our health and our quality of health, but like you said, this was the king of Saudi Arabia. He was bringing in a lot of the physicians from the U.S. They were flying him in to treat the king, basically.
Yeah. Well, this is amazing. Okay. I love your story, and I can't wait to see the advances that you and your lab are going to do in the future. Thank you so much for taking time out of your day to share your story with us.
Yes. Well, thank you very much. I really enjoyed the conversation.
That's it for this episode of HolyShift, Biomedical Breakthroughs Shaping Tomorrow. If today's conversation sparked your curiosity, pass it along to someone eager to explore the power of research to change lives. As a reminder, the opinions expressed in this podcast are those of the host and guest and do not represent those of any organization mentioned. Be sure to follow or subscribe wherever you get your podcasts so you never miss an episode. To learn more about the research featured on this show, visit bme.gatech.edu or check the show notes for links and resources. Thanks for listening, and remember, behind every innovation is a purpose, a person, and a powerful story.